All right, welcome to our very first video lesson for honors trigonometry. We are going to start into the book in section 2, as section 1 is kind of, not that it's not necessary, but it's kind of just a little section that we're going to just omit for the time being. So you'll notice there's a little A next to this. What I'm going to do is I'm going to split section 1.2 up into 2 separate lessons because it's a very large section, has a lot of key definitions and key points that we really need to stress. So I'm going to break it into 2 to kind of chunk it up here. All right, so we're looking at functions and their properties. What do they have? What can we do with them? So here's the main things that we're going to cover in chapter 1, or in section 1.2. And this is actually all the stuff we're going to cover today in this first lesson here. So we're going to be looking at what are functions, how can we find their domains and range, looking at what continuity means in the terms of functions or graphs, that sort of thing. How can we find our asymptotes? We're looking at what does an increasing and decreasing function look like? What does boundedness look like? Where are minimums and maximums of a function? And then what are even and odd functions? And how do we find them? All right, so a lot of little things to cover, and there's even more than that as we're splitting it into 2 sections here. So let's go ahead and start with domains and range. But what I'm going to first start with is, what is a function? How do you know that you have a function? Well, if you're looking at an equation, equations are usually just in 2 variables. So this is an equation in 2 variables, or as the book likes to say, it's a formula that determines y as a function of x, because you can write it as y equals the x squared. A non-function might look something like this, where this tells me it's a function, or x is a function of y, not y is a function of x. And this would be a non-function. And we'll get to that type of equation a lot later in this book. And graphically, you might remember from your Algebra 2, in order to find out if a graph is a function, you get to use the vertical line test. So if I was to give you this graph here, you could tell me that it's a non-function because a vertical line goes through and it touches more than one point as that vertical line goes through the graph. Whereas a normal quadratic will only touch once. And that would be a function. So this is a yes and this is a no. All right, the other stuff that we need to cover here on functions is the fact that the domain of a function, we call it the inputs of the function, also better known as the x values. And what we're basically looking for is anything that I can plug into an equation. If we go back to this y equals x squared plus x minus 1, I can plug any number ever, any number that I can think of, I can plug in for x here. However, a function like this, I can't plug in 0 because I would get out 0 in my denominator. So x would be, or 0 would be excluded from my domain, but I could plug in anything else. Range is defined as the outputs, or in other words, the y values. What are the possible y values you're going to get on the graph? The domain can be found usually very easily through algebra. We can find the x values algebraically, what we can and cannot use. However, the y values are normally graphically. So we're going to need to know how to graph a function and use some of the basic ideas on that graphing calculator, which we will go over in class. My tip for finding domain is to basically figure out what x cannot be, because that's going to be a little bit easier. In the case of y equals 1 over x, x can be anything, but what we're going to say is x can be anything but 0. So we can write our domain based off of what x cannot be. And you'll get more the hang of this as we get through the examples. And there's what I was just saying. The tip for finding the range is doing the graph, or sketching the graph, or drawing the graph on your calculator or on Desmos. And what we are doing is we're going to use that interval notation that we've been doing in class with our inequalities, such things like -1 to 3. This obviously is representing this statement right there. X is between -1 and 3. If we wanted to write the domain for this quadratic, there's two things that I will allow you to write. So since we can have all real numbers, we have a symbol for all real numbers, and that's represented by this R right there. It's a double bar R. It represents mathematically stating all real numbers. Or you write it in interval notation from -infinity all the way up to +infinity, like that. This would be my domain of the quadratic function there. The domain of this y equals 1 over x is a little bit different. I can't say all real numbers because that's not the domain. But I can say it's everything starting from -infinity, going up until 0, can't be 0, so I have to jump over 0, and starts at 0 again, goes up to infinity. This statement right here says everything except for 0 because of the parentheses. All right, so I do have some examples here for us. First one being x squared minus 3. This is a simple quadratic function. That quadratic function, since it's a quadratic, it's a polynomial, and all polynomials have the domain of all real numbers. The range, however, you might want to think about this graphically. X squared minus 3 looks like this, where this point is -3. And we can say that there are no y values below -3 because we know how parabolas work. But our range is going to start at -3 and go all the way up to infinity, because my y values will always be increasing, will always be going up. All right, something like 2 over x. 2 over x, the domain is going to be like the problem on that last slide, saying x cannot be 0. So we're going to say it's everything except 0. Now the range is a little bit interesting. Graphically, this looks like this. Notice that there's that vertical asymptote, which we'll discuss later, at 0 because x can't be 0. And what you'll also notice is that the y values will never be 0. So my range in this case starts down here because the arrow's going down. So it's coming all the way up from -infinity. Remember, this is y values. It's coming up. It's got to jump over 0. Can't be 0. And it's going to start again on the other side and go towards infinity. So you notice in this case, the domain and the range are exactly the same, and that's only on special cases here. Okay, next example we have here is the square root of x plus 3. Now, we should know that we can only square root positive numbers. That means that x plus 3 has to be bigger than or equal to 0. And if we solve that, we would say x is greater than or equal to negative 3. So that means my domain starts at negative 3 and goes towards infinity, being greater than or equal to 3. And we've all passed algebra 2, so hopefully we know what x plus 3 under the radical looks like. It gets shifted 3 to the left and looks like a shooting star sort of thing. Notice my domain started there at negative 3. And you'll notice that the range starts at y equals 0 and always increases forever. So my range is going to be from 0 to infinity because that's the only y values that exist. Oh, then we can get something like this. This looks a little bit more challenging here. And it is. So right in here, we have the square root of x over x minus 5. The x minus 5 is not under the radical. So we need to think about what x can be. So this piece here says x greater than or equal to 0. But this piece here, because it's in the denominator, x cannot equal 5. So if we set up our domain, we need greater than or equal to 0. So we can start at 0. If I said infinity, I would be wrong because I can't let x equals 5, and that would be included. So I have to go up to 5, and I have to jump over 5, and then go to infinity. And then the range is going to come from graphing that function. So I'm going to graph mine really quick on my calculator. Maybe you should try to as well if you have one. And on our calculators, we get something that looks a little bit like this. And there's x equals 5. And we'll notice that the range, it will go infinitely down, so it'll start at negative infinity. It looks like it jumps over 0. Looks like there's a horizontal asymptote at 0. And then goes to infinity. So you just have to be able to look at your graph and say, what are my possible y values? What are my possible x values? Last one here, I'm going to erase my screen from all of this stuff. Last one here is a real world problem. This one says that the m, or the area of an equilateral triangle, is determined by this formula, root 3 over 4 times x squared. And I want to find domain and range. Okay, so domain is going to be all possible x values. Well, it's a quadratic, so we would think it's all real numbers. But the problem is it's a real world problem, and if x is the length of a side, x can't be negative. But I also like to say that x can't be 0, because then we wouldn't be dealing with an equilateral triangle to begin with. So let's say it's got to start at 0, kind of, and then go to infinity. That would be my domain for this real world problem. And my range, it's a basic quadratic. It starts at 0 and goes to infinity. But because I don't like a 0 area, we're going to say it doesn't include 0 and going to infinity. All right, let's move on from domain and range. You'll have plenty of examples to study this. Continuity is a somewhat easy statement. You can either be continuous or discontinuous, or not continuous. And a continuous function, or a continuous graph, is one that has no breaks. I basically say it's one that you can just draw without ever picking up your pencil. You'll never have to do any jumps or anything like that. Where a discontinuous graph would have something like this, it would start go along, and then you got to do this, and then you got to jump down here for an asymptote. You can have a little dot and go like this. You can say this. That would be a non-continuous function. And I'm going to keep that graph there because I want to talk about the different types of discontinuity. The first one is being removable. This is a removable point of discontinuity. And it comes from factoring and canceling in a rational function. A jump discontinuity, kind of exactly what you would think. This is a jump. And lastly, we call the asymptote one an infinite. This is an infinite discontinuity because it infinitely goes up and infinitely goes down. And those are our three different types of discontinuity. And it all comes from the domain. What can x not be? That sort of idea. So if I was to determine the function of continuous, if not, find the points of discontinuity to determine the type. So x plus 3 over x minus 2, my point of, or my discontinuity is going to be at x equals 2. And if you graphed this function, you would know, or you would see, that at x equals 2, there's a vertical asymptote. So this would be infinite at x equals 2. It would be an infinite discontinuity at x equals 2. This one I purposely put like this. Notice that it's x plus 3 times x minus 2. Well, this is just x squared plus x minus 6. That's just a quadratic. So this is continuous. All polynomials are continuous. And last example here is going to be x squared minus 4 over x plus minus 2. If I factored x minus 4, I could cancel out the x minus 2's. And because I canceled, this now looks like x plus 2. But x equals 2 is a point of discontinuity. But because I canceled, it's removable at x equals 2. And if I wanted to know where that hole is at, just like on that last graph, it's got a hole at whatever I plug in x equals 2. If I plug in x equals 2 to this, I get 2 plus 2, which is 4. So the hole would be at 2, 4, the coordinate 2, 4. Very straightforward. Once you remove it, you plug it in to see what that hole would be at. So if I graphed that function, it would look like x plus 2. However, at x equals 2 and y equals 4, there would be an open dot right there. That would be a removable discontinuity point. All right, like I said, there's a lot of little things that we need to cover in this section. So the next one is boundedness. A function is bounded below if the entire graph never goes below a given y value. And that value is called the lower bound. So a very basic example would be a quadratic, a positive quadratic. This quadratic, let's say that vertex there is at 1. This would be called bounded below at y equals 1 because it never goes below the value y equals 1. So we'd say it's bounded below at y equals 1. And that goes the same for the other types of boundedness. I'd say bounded above if it never goes above a certain value. I say something like this. Right here, let's say that y value is 3. This would be bounded above at y equals 3. it never goes above the value of 3. But then we have our last one, which is bounded, saying that it is entirely between two values. And we're going to get very familiar with a set of bounded functions. This is the sine function from -1 to 1. We say this is bounded between -1 and 1. Or bounded above at 1 and bounded below at -1. And that entire function will never go above or below those two numbers. Unbounded would be something like a cubic function. A cubic function goes like this. It will always go negative and will always go positive, and therefore it is an unbounded function. So anything like an odd function like that, odd power. Okay, increasing and decreasing. Increasing and decreasing parts are just intervals of x in which the y values are increasing. Let's just look at a basic quadratic. And say at x equals 1 is where my vertex is at. This quadratic is increasing from 1 to infinity. And if I continue this, it's also decreasing from -infinity to 1. So you notice the function is going up after x equals 1, and it's going down. Remember, we read from left to right. So going from the left here, it's decreasing, and then it starts to increase, and it's all based off that vertex. And constant just means you have a horizontal line. You could get some sort of weird function that looks like this, kind of comes up here like this, goes like this, goes like this, and then it comes straight across, and then it does this. So we would say it was constant from A to B here. Not very many functions are constant like this, but you can have it. So here's our first assignment. I will have an assignment sheet ready for you guys tomorrow. So you can start on this if you have a chance. I'd prefer if you started it before you got to class, so if you had any extra questions. We really need to focus on this first chapter because it really bases all of our study of functions. All right, I hope you had a good time and learned something. I will see you guys tomorrow.